more so rotational motion. So the basics is forces about a point of rotation is equal to rotational motion. And so right here it says the sum of the forces of force times distance perpendicular is equal to the inertia of an object, right? So this is force times distance perpendicular, this is inertia, and this is angular acceleration. Some people put theta double dot. All right, and then right here, I have this point of rotation right here. Oh, I could do one here as well. And so it's saying, what would be the torque from each force. So I guess let's say this is F alpha. So the torque from F alpha would be 0 because this is a force perpendicular. However, there is no distance from the point of rotation, so it'd be F alpha times 0, which is 0. And then right here, F gamma is also perpendicular from the point of rotation, right? It's point right here. And so the distance itself is L, so the torque from that would be F gamma times L, which is, I don't know, a number. And then for F beta, the force acting on the point of rotation is not perpendicular, and so therefore there'd be no torque generated, right? You could think about it if you were pushing a door from the top of it, I guess. Like you're not going to open a door from that angle. You could push it from the side, but you can't open a door from the top of the door, if that makes sense. And I'm not talking about the top portion of the door. I'm talking about like the actual roof of the door. Anyway, and so we'll have this somewhat basic problem, and we're gonna move it to the side like here. So we have one spring. Shoot. We have one spring here. We have the full length of the bar here. We have half the length of the bar, and we have the point of rotation here. Now, it's our assumption that the center of gravity of this bar is going to be in the center. Oops. In the center here at L over 2. There's also some very important assumptions we're going to make for vibration specifically and rotation of this bar. A, that it's a small angle, right? So this thing's only going to oscillate between around 15 degrees in this like general direction. That's a very important assumption. Uh, Assumption 2, that this is a rigid body, right? This is not going to behave weirdly when we start moving it. Uniform density, frictionless, linear spring, gravity is pointing downwards, that positive theta is going to be counterclockwise, and the spring is unstretched at theta equals 0. All right, so let me repeat that. Small angle, rigid body, uniform density, frictionless, linear spring, gravity pointing down, theta positive at counterclockwise, and spring unstretched at theta equals 0. Very important. So with that, let's go on to this one. So let's say we move this is more pronounced. It's supposed to be a small theta, but pretend it's like a very small rotation. But this is more pronounced to make the problem less cluttered. So let's just start off with what we have. So we know that there's gravity acting on the object, and I'm going to be using blue as our forces and red as our inertia. So there's gravity acting on the object. We know that from the point of the center of gravity. Simple enough. And it's pointing down, so I'll call that mg. And then since this object is moving this way and the spring's here, this spring is going to be a little compressed, and a compressed spring pushes. Therefore, there's going to be a spring force going this way. And then there will be some reactionary forces at the top. But since we're more worried about the moments, these are not going to matter anyway. But, for conception's sake, I suppose. And that's it. Now we can worry about the inertia of the object. Alright. So this thing's moving this way, so there's some sort of torque being applied. And I'll do it here, but I kind of don't use it, is that since we're counting this as a center of gravity, there's going to be a force going this way in the x direction and a force going this way in the y direction. And that would be all the inertia. And then this is moving some angle theta. Right? And then I redrew it right here. Is that better looking? I don't know. So, and then I also redrew it again and made it a little more pronounced. Again, it's a small angle assumption. And I think it's like smaller than 15 degrees is a small angle assumption. And typically for this thing, it's like, let's say it's like a building. Like a building's not going to oscillate more than 15 degrees, so that it's a realistic assumption. Or like a little pendulum. It's not gonna swing that largely. And we use this assumption so that we can make cosine of theta. If it's a small angle, we can assume that it's equal to 1. And sine of theta, if it's a small angle, we could just assume it's theta. That's why we're using that. Maybe I should have kept it up. I don't know. So from this, let's do our our equations. And then let me just remind you. It's going to be this. Why is it doing this? It's going to be this equal to this. So we'll start with this side first. All right, so some of the forces, it's going to be Fs. Oh. It's going to be Fs. And then this force is going to try to push the rod this way, so clockwise, so it's going to be negative. Times x, how much the spring is compressed. And then times the distance from the point of rotation perpendicular. And so the distance from the point of rotation perpendicular, let me use pink, is going to be this length right here. Right? Because we're not counting the whole length, because that would not be perpendicular. We're counting the vertical length itself as the perpendicular length. So now we got to do some trig. Let me get rid of that. And so this length will be, we know this is L. If this angle is right here, then this angle is also right here. And so this length right here would then be L cosine of theta. So that means we know this is L cosine of theta. And then let me just get rid of everything so it's beautiful. Bam. L cosine theta. And then I'll explain what this x is in a bit. Alright. Now let's deal with mg. Mg is also going to act in a way that it forces the rod to be clockwise, so it's also negative. So negative mg. There is no x involved. And then what's the distance perpendicular of this? It's going to be this x distance right here, which we know this angle theta, so it's going to be sine, and we know this to be L over 2, so that means the distance from it is going to be L over 2 sine of theta. Yeah. And then we have these reactionary forces, but they act at the pivot point, so they don't matter. And that is it for the sum of the forces times perpendicular force. So I'm gonna grab that and sort of just move it right here for now. And then let's do the inertia. Now, for this problem, since it's somewhat simple, I did it one way. But I saw a different way to do it, so I'm going to do it both. I'll do it my way first, and then I'll show the other way if you want to do it that way. So, again, let me remind you that it's equal to I alpha. And then if you know I off the top of your head, then you could kind of just skip the steps for this. So, now let me use red. So the sum of I alpha, there's only one kind of, it's right here. You only really got to worry about that one. So it's going to be equal to I, which is 1/3 ml squared times alpha. And that's pretty much it for this one, because this is the inertia for a rod about a point from one of the ends. And then alpha, if you recall from, I don't know, physics 1, is equal to A over R, which R in this case is just L, so it'd be A over L, and then L cancels, and so it becomes 1/3 ml times A. And that's that. Or you could keep it alpha, so 1/3 ml theta double dot, so that should be squared. Either way, that's pretty much that. But, so that's the way I would do it, personally. But, you could also do it this way. So it's going to be sum of I alpha. And then, so the other way the teacher did it is I center of gravity is going to be I center of gravity times whatever alpha, bam, plus this, which is going to be MAX times whatever, let's call it D1, plus MAY D2. So now this is taking the inertia about this point. It's going to be about this point, but it's taking into account everything here. So this is the inertia about the center of gravity. This is the acceleration of that point in the x direction. This is the acceleration in the y direction. And you're about to see why I didn't have to do it this way. So the inertia about the center point is going to be 1/12 ml squared. That's m squared times alpha. MAX D1, this is M. A is equal to alpha over L. Maybe I should have wrote that on the side. Oh no, it's alpha times, it's R. Alpha times R. But in this case, we're working from the center of gravity, so R is going to be L over 2. No. So let me get rid of R. So alpha L over 2. And then D1 is going to be the perpendicular force, or this column right here, which is going to be L over 2 cosine theta. Oh my. Okay. And then MAY, we're assuming this point, I mean, it doesn't really help. Like, but for our assumption, the small angle assumption, we're assuming that this thing doesn't go up or down linearly. So, because if you think about it, for all these problems, once you turn the spring force is actually going to be acting on like this angle right here, right? Because if I stretch it right here, the spring is going to be this way. If I move it this way, then the spring is pointing at an angle. And so for all of our assumptions when doing these kind of problems is that since it's such a small angle, the I don't know, what's the word for up? The longitudinal change in distance doesn't matter, so it's negligible. Therefore, we can ignore MAY. So, we have this now, and, you know, long story short, this equals 1/3 ml squared times alpha, which of course equals 1/3 ml times A, because A is equal to alpha times R, which why does it look like that? Okay, A is equal to alpha times R, and the total torque of this thing, R, is just L, so pew. Bam. Am I making any sense? I don't know. So this is this side, and we have this side, so that we set them equal to each other. My dog is at my door. So bam, sum of the forces perpendicular, and then sum of the inertia. I'm just going to use black now. So it's going to be negative mg, I already forgot what it was, over 2 sine theta, minus spring force times x, which I'll get to in a second, L cosine theta, which equals 1/3 ml, 1/3 ml squared alpha. You know what, we're going to use this because that's what they like to see. Now, let's put this all to one side, so you get 0 equals 1/3 ml squared theta double dot plus mg L over 2 sine theta, which I gotta get rid of, plus fs times x L cosine theta. This would be kind of a finished problem, but there's ways we could simplify this, as I said before. So let me grab Dosh. Because we're using the small angle assumption, sine of theta just becomes theta. Cosine of theta just becomes 1. Yeah, that would be that. So let's rewrite this. 1/3 ml squared theta plus mg g L over 2 theta plus fs x L. That's it. All right. And then there's one step left that we have to do to solve this. We do know x, but we have to rewrite it. So x, because it's it's a circle, if you recall, the linear distance of a circle in terms of this is equal to r times theta, right? This is a circle. This is the linear distance of that like corner piece of the circle, and this is theta. And we know r to be L. And so this is how much the spring would compress, right? Because like if this is the neutral part, it moved this much. That means the spring compresses this distance to this distance, right? Which we know the formula for that would be x equals r times theta, or x equals L times theta. So then we could replace x with that. It increases. So it's going to be 0 equals 1/3 ml theta. I'll just write right here, mg L over 2 theta. This is theta double dot, oops, plus fs, I forgot, x equals r times theta, L times theta, L theta times L, or just L squared, let me get rid of that, times theta. And then is that correct? Let me look at this. No, 1/2 mgl theta, 1/2 mgl theta, that's correct, plus k L squared theta. Okay, I made a mistake there, but I'll come back to that in a second. Times 1/3 ml squared theta double dot. Okay. Okay. How long is this? I don't know. Do I want to redo that? Okay. Well, I made a mistake. I kept on saying fs. Fs. Fs, I meant to say k. This is supposed to be k. Everything here is supposed to be k. Oops. This is right. This is fs, but fs is equal to k times x. That's supposed to be k.